Good morning. I'm so happy to see you. I'm so happy to be here and talking about math. So I'm very excited for my trip, which I'm going on tomorrow. But in the meantime, I was just thinking about Em a little bit. I was like thinking about it a little bit while I was like doing laundry and sitting in the car waiting for the laundry to get done in different moments throughout the weekend. And I really wanted to think about I'm thinking about these prime blocks again. Sometimes I think about it and it's like it's so dumb. Like it's so there's nothing there. Like, why do I keep talking about this? And then sometimes I'm like, it's so interesting. It's so interesting. So I guess what I wanted, this idea of this weekend, or just working on this lately, just like a little something before I go on my trip. I wanted to think about like, what is Em really? Like, besides my opinions of it and like what I might put on it, like what is it really? Just what are you? How do you work? Like reveal yourself to me. Like, okay, so I just wanted to figure out, or just think about what Em actually is, and I think this would still be an interesting paper. Like, if there's a philosopher, because I feel like there's a lot to say. Because I'll write stuff out, and there's a lot to say. So like, at least you have that. I mean, at least you have something to say. I don't know if it's interesting, but I just feel like there's something there. Okay. So I really want to know about Em and what it was actually like. And so let's pull up the slide. So I think actually that Em is like a model of piano arithmetic. I thought it was very different. So let's pull up the first slide. I thought that is a very different, even especially the ones with the missing primes and whatnot. But I think that actually they're really just like, from our point of view, they're just models of arithmetic. Like they might themselves, they have addition, they have multiplication. We'll talk about the multiplication today. They have all that, but to them, like, oh, here's the only thing that might be really different is that to them, like, they really have two different representations for 6. If they have both of those primes, 2 and 3, then to them, they really are different because they're different structures, because they care about the structure of these numbers. Like in their world, they care about this object, and like we don't care about that. We only care about cardinality. So like, even though to them they have these two structures for 6 with a 2 base or a 3 base, to us they're really the same. We might be like, they might think of those as different, but as far as us and how we think about numbers, like it's still 6, and then we don't really care about that. We only care about the cardinality of it, really. I call them the Emmians. To Emmians, things are different, especially M to the minus P, where P is a prime. But even M to the minus P, we still think of it as a model of arithmetic because they still have the prime. It's just that it's like this. They can still do everything. Okay, so I think that my latest is I think that M is actually a model of piano arithmetic, and so are all the other ones. So are all the weird ones. Even if you knock out 2 primes, I was like a little worried about that. What would happen if you knock out 2 primes? But I actually think that, I don't know. That's just for now. This is pure fun, It's just for pure fun. Okay, so number 2. What is M really like? Yeah, I really want to think about what is M really like, despite my preconceived notions of M or what it should be. Okay, so to them, A plus B equals C. Adding amounts to busting up. I call it busting up the individual blocks and to form C with prime blocks. So whatever you're given and it doesn't matter if you're adding, you're just given these two objects. If they happen to already have the same prime base, then you can just stack them on top of each other. But most of the time, you'll be given things with different prime bases. And in that case, you just bust up both of them. In like that little game I was playing, you just try it with base 2, base 3, base all the prime bases. Eventually, you'll hit one, or it'll be prime itself. Okay. For multiplying, we need to like order more blocks for the construction. For the adding, you have all the blocks you need. For multiplying, you need to order more blocks. Okay, so let's go to slide 3. Okay, so slide 3, let's say we're doing multiplying in M. So suppose you're given that the first thing you're given is a prime and multiplied by, or one of them is a prime, multiplied by a composite. If that's the case, then you already know the prime block you can use. Then you just bust up D, into pieces and make it a height. Now, they don't think of these heights as like building blocks or anything. To them, that's almost an abstract concept. And I kind of wanted like the paper to involve that, like this idea that to them, these heights are sort of abstract concepts. They do actually have, like, they take the height D. And I was thinking about how they do this. This is what they say. So they take the height D, they bust it up D, and they just make it like a height so you can see how many more prime blocks you need to order until you get to that height. And again, they have this idea that like, and I don't know why they need to have this. It doesn't seem like necessary, but it's just interesting that they don't really need to count anything. It's not like they could, some world could say, okay, you have this block and this block, okay, count all the individual pieces, see what that number is, and then go look at what structure that should be, and then pull that structure in. But this is somehow, they don't have to do that. That seems harder somehow. This is just like, okay, I just take this, like a child could do it. You take the D, and you bust it up, and then you make a height. Okay, so the heights, again, I think these are sort of abstract concepts to them. The height is sort of an abstract concept. I mean, they can build it, and then they fill it, and they say, but they don't really think of that height, that thing that you built, as like a structure, as anything. It's more like scaffolding, because it's like, it's going to be going away. That's not an actual thing you build with. So to them, the things that are really real are the things that you build with. So that thing where that structure that you made, that H, that's just like a scaffolding that you hold in place until you figure out. Okay, they didn't really have to count again. They just had to, I don't know why that's important. Okay, so I do like this idea that somehow in this world, they have two concepts of number, and one is like a prime block, a very solid physical prime block, and then there's like these heights that are the more abstract, even though it's still sort of physical to them. So it's not that abstract, but it's still sort of a different concept. But to us, it doesn't, to us, it's just like, in the end, you give me this rectangle, I know that this is P times D. You got the thing. And I know that this is one of the structures in M because it has a prime base. Okay, we'll go to slide 4. Okay, case 2, let's say you're given two composite numbers in M. So you can just choose either prime base you like. In this picture, I chose C, and so I just take all the prime blocks that make up C. So there's like maybe several, whatever the decomposition of C is P times some height. So whatever one of its prime blocks is, you take however many. It's right there. You don't have to really like think that much. It's like I have these C that's made of these prime blocks. I take each prime block, and then I bust up D. And then make heights, make scaffolding for each of those, and then fill in, order more. We need more prime blocks here, prime blocks here, prime blocks here, the dozers. And they fill up all the heights, and then stack them all together. And now you've got P by, like H by D or something. Like you've got the full multiplication. Okay. Then stack on top of each other. Okay. So let's go to 5. Okay. For example, 2 times 3. Okay, so I took the 4 times 6, 2 composites. So I took the 4 and I took the prime blocks. So these are already, I can't just stack them on top of each other. That would be adding. I'm sorry, I still need to do this. Okay, so I take the prime blocks for 4, which is 2, and there's 2 of them. And then I bust up that 6, and I make those as heights scaffoldings, and I fill in an order up, and I order all the prime blocks I need. In the end, I put those 2 together to make 24. 2 by 12. Okay, so let's go to 6. Okay, so I feel like even in M to the minus 2, it's still a model of PA. I would absolutely. I think like there's some people at this conference that might know about piano arithmetic. Listen, there's a lot of people that know a lot of things. But I mean, if there's someone that like knows like a lot about piano arithmetic or like to talk about piano arithmetic a lot, maybe they want to talk to me. Okay, so let's say I think even in M to the minus 2, it's still a model of a piano arithmetic. Okay, so let's say we're given 3 times 2, and we have to do the arithmetic multiplication, but we're given 2 has been relieved of its creative abilities. It's still a number because we need the number 2. But what's 2 times 3 in this case? In this case, it's great. Okay, you have the 3 base is already there. Even if it was a composite number, whatever that prime base is, you can do multiple of them. But in this case, it's just a prime, so I just do 3, and then I get the height, it's already there, and then I did 2, and I can do 6. It's no problem. Then I was thinking, what about if you had to multiply 2 by 3, and you were in a world where 2 and 3 were not, the primes were relieved of their creative ability? Well, in that case, I would say that in that case, 6 is prime. So I'm not sure how they do that, but I think there's a way. I think that there's a way for them to know that, like, well, I guess you could say this. If you're given 2 verticals, then you know. If you're given 2 verticals, well, if you're given 2 verticals, then their product has to be prime in this world, because you're given 2 verticals. Like, if you are a, let's say, like a semi-prime is right. You're like a multiple of 2 primes. If those primes are sort of dead in this world, I'd like to stay positive, but sometimes, you know, sometimes things get eliminated. But I would say that you know that those somehow that's actually an easy case. At first I was thinking this whole thing falls apart at this, but like if you're given 2 verticals and that's it, then that has to be prime. So like you have to just figure out what that prime number is. You know, maybe you can temporarily hold off on this. I don't know. I actually think that I don't know. I don't know the answer to that. I don't know. I think that though, that if that's the case, you know for sure, if you're given 2 vertical blocks, you know for sure that the result is prime. So maybe they lay down the blocks that they need and then just make it into prime block, because it's not going to stick. Like in that world, if you try and like use a 2 block, maybe you can put them next to each other temporarily, but it's not going to like stick. And I think of like when a prime block shows up, it's sort of like lit up, and it's like lit up and it's stuck together. Okay. Once again, I'm going on for a while about this. Okay. So I think it's possible, but yeah, I'd like to talk to it. I think that even in these worlds, it's still like a model of arithmetic. Does it have the same primes? Like that's I don't know. I don't know. That part I don't know. Like to us, is it 2 really a prime there, you know? To them, it's not, you know. They don't, it's very solidly not a building block. And you can get around it. I think it's really interesting that even though you have these sort of like dead primes, you can still make all the numbers. Okay. Finally, we'll go to 7. Okay. The conjecture is that m to the minus 2, m to the minus p, n to the minus pi, pq, they're all models of Peano arithmetic from our perspective and our interpretation, and we can interpret PA and M. Because I'm not always sure what I'm talking about, like if I'm actually saying things correctly. Like I think we can interpret PA and M because we just did it. I just used like, I'm doing it by making this world. Next, we can see that like the distributive laws hold. I think that they do, but maybe that's interesting. It's going to be interesting to see that. Because we got the addition, we know what to do, we know the multiplication. Okay, that's it. So that's it for today. Okay, I'm going to be going on my trip. Maybe I'll say hi over the trip. I don't know. I don't know how busy I'm going to be on the trip, but I'm definitely going to just be going with the flow, and hopefully working on this stuff and working on different things, and hopefully maybe working with people. That would be the ideal outcome of the trip. Okay. Okay, everyone. I don't want to say goodbye because it's just my favorite thing to be here. Okay. Well, I'll see you soon, and I hope you have an excellent day of mathematics. And if anyone is traveling or going to conferences, also for other things too, I hope you have an amazing and fruitful conference, and you meet a lot of nice, smart people. Okay. I'll see you guys soon. Okay. Have a great day. Bye.